it's a good idea. It may be, because what you see here is that the small bugs have highest effect size. Right? So as you go larger, the effect sizes are smaller. So the small bugs show the biggest effect size. Okay, so this is what I like the most. This is really interesting. Okay, so with every bug, there's a latency, right? So once you buy into SCZ, I mean SCZ, there are some critics of SCZ, right? But once you buy into it, if you really believe what it's telling you, right, then you can measure the latency of bugs, right? So a bug introduced here from git blame and fixed here, because SCZ will tell you those things, right? So then you can look at the latency of a bug. There are short latency bugs here and high latency bugs that take a long time to fix. Okay? So this is interesting. The short latency bugs have high entropy difference. That is, the sooner the bug is fixed, the more likely I think that it's a stupid mistake. Right? So these things get very high entropy differences, and as you go higher, it's not as strong. I thought this was very interesting finding. So this is in ICSI this year. So this is from ICSI in Austin. The first author is Baishaki Rai, one of my other postdocs who did this. That was quite interesting. So this is another take on the same data. Yes.
But what about injecting new bugs? So this would increase the entropy soon after a bug is done. Yeah? So you have a bug, and then you say that after I remove the bug, I fix the bug, the entropy goes down.
Generally speaking, yes. Yeah.
But we're being told that careful of injecting new bugs when you fix one bug. Right? So you should have seen some kind of increase of the entropy, or perhaps you don't see it soon. You see it later.
I see. So what you're saying is, if you look at those cases where bug fix introduced new bugs, the entropy is not coming down as much.
Yeah.
I haven't tried that. Interesting idea. It could be. Interesting idea. We have the data. Other comments? Okay. This is interesting. So this is not your typical defect prediction technique, right? Your typical defect prediction technique works at the granularity of files, sometimes methods, but mostly files, right? So it's like, I'm going to predict this file is defective or this module is defective. Sometimes method is defective. This is different because it's predicting defects at the line level, right? So essentially predict average entropy per line, right? Use that to measure line level predictions. So the normal measures that are used for defect prediction performance are precision and recall, right? Sometimes AUC, which is a non-parametric measure. But I think at this point we should stop using precision recall. We should use AUC because AUC is not parametric. But that's not suitable here because those are file level. This is line level, right? So we have to use a measure that's line level. And so the best measure, to my mind, that is a line level measure is called AUCEC, area under the cost effectiveness curve. How many of you have heard of that? AUCEC. Oh, good, thank you. So this is from Arcodi and Bryant.
There is.
Ah. So the AUCEC idea is again, it's another plot. Okay, so the idea is 0 to 100%. Lines inspected. So it's all about inspection. Why inspection? Because the idea is what defect prediction is telling you is where to focus human effort. It doesn't tell you anything about, automatically find the bugs. It tells you, look, we think this is the most likely location to have errors, so you should focus your effort here. Right? So it's all about inspection effort. So this is you inspect none of the code, this is you inspect all of the code. Right? And the y-axis is 100% of the lines discovered, or none of the lines discovered. Okay? So if I have a perfect defect prediction algorithm, which is going to tell me exactly which lines are defective, right? Then basically, I only have to inspect those few lines, and I find all the bugs. Right? So I'm going to saturate very quickly. Right? So the area of the curve is close to 1. So this is area under cost effectiveness curve. So it's also known as AUCC. It's actually very simpler to understand than AUC, I think, than area under curve. AUC ROC, the receiver operating characteristic. So this is like a very good inspection algorithm because a very good prediction technique because with the few lines you can find it right. So if my method is absolutely no better than random, what would the curve look like? It's just a, just might as well choose lines at random. What would that line look like? Say it again? Well, okay. So let's say, averaged over many possible trials, right? Randomly choose lines, but do it many, many times and average, what would that performance look like? If I inspect 10% of the lines, on average I will find 10% of the defects. If I inspect 20% of the lines, on average I will find 20% of the defects. Averaged over many trials, randomly choice. So random choice over is going to be a diagonal. So the area under this cost effectiveness curve is about 1, and this is a really good one, it's going to be about 1.0. Okay. Now, this is not really the greatest measure because most of the time you're only going to inspect about 5% of the lines. Right? Inspecting more than 5% of the lines for a big project is not realistic. Right? So if your curve, looks like this, right? It's not very useful because you're never going to inspect this many lines, right? So this is just as actually worse than random, right? For a 5% budget. So AUCEC is always evaluated with respect to a budget, right? At 5%, how high are they getting? And how much better are you doing than random? That's what most people look at. Okay? So if you have a curve that looks like this, with 5% you're getting very high effectiveness. So it's good, right? So if you have a diagonal line at 5%, you're not doing too well, right? So you're always comparing it to the diagonal. So this area here is 5% times this area. We want to do much better than this area here. Right? So this is the measure we have to use. Why? Because we're recommending lines to be reviewed at the line level. Because we're scoring entropies at the line level, we're saying which lines you should focus on. Okay? So that's what we have to do. Now, the interesting thing is, tools like find bugs, PMB and those kinds of things, are also going to warn you at line level. So we can compare what we're doing to static analysis warning tools. Right? Because we're at the line level and they're also at the line level. Right? So static analysis tools tell you which line to examine for defects. If they're really good, then if you just look at those lines that are being warned, you're going to find most of the defects. Right? But most of them, of course, they have a lot of false positives. They're not going to be really good. So we can compare ourselves to them. We'll take 5% budget and see how well we do compared to static analysis warnings. This is not entirely fair. You see why, right? Because the static analysis tool will tell you this is what I think is wrong, but we tell you nothing. We just say this looks weird. Right? That's all we can do. One thing we could do is better is we could say this looks funny. Maybe you meant this because this is similar but looks somewhat different. That would be better. We don't do that right now, but this is something we're going to think about. Okay, so everybody clear on this cost effectiveness curve? Okay, so just to summarize our findings, if you compare ourselves with the normal defect prediction using logistic regression, where basically these things are arranged, entire files are being predicted, you arrange the files in decreasing order of probability of defects, and you see how well that does. We do more effective than the best available logistic regression-based defect prediction methods at 5% inspection budget. So at a small budget, which is a realistic budget, we're better than that. We're not as good as logistic regression at 20%. The cost effectiveness is similar to find bugs and PMB. Okay. Now, this doesn't sound that good from one argument, which is that we don't say why you should look at the lines, whereas find bugs and PMB will give you specific warnings, right? On the other hand, we don't know if those warnings really have to do with the bugs, because that requires manual examination, we don't know that. And on the other hand, we don't require parsing, we don't require type checking, we don't require data flow analysis, it's just token level. Right? So it's very easy to port what we have done in different languages, because it doesn't require any additional intelligence of what the language, except from the tokenization application. Whereas find bugs and PMD are all specific to Java. They will not work for C and C++. Okay, so, and the third finding that was kind of interesting is, if you take the warnings provided by find bugs and PMD, and you order the warnings by the entropy scored on those warnings, then you do better than find bugs. So we can actually take find bugs and PMD, which produces some ordering of the warnings. You can improve the ordering of the warnings by putting entropy on top of it. So if you put that, then actually you get steeper curve from find bugs and PMD. So that actually works better than both. So if you combine the two, it works better than both. Okay, so I have a couple more interesting applications of this area that I want to talk about, and then if we have time, we'll get into some more NLP modeling stuff. All right, so this is sort of a grand vision for the area. So there's a bunch of projects going on, so I would say there's activity in this area, a lot of different universities at UC Davis, at College of William and Mary, with Dennis's group. There's work going on at Iowa State, and there's some work going on at the University of Washington. A bunch of work at ETH. ETH is very active in this area. University of Edinburgh, some activity at University College London. So there's a lot of people working on a lot of different aspects of this, but there's a lot to do. And so, I encourage you to get engaged in the area. There's a learning curve, it's not that easy to get into it because you really have to learn NLP. So if you're in grad school and you have access to some good courses, please take them. And then there's a lot of interesting stuff you can do. You'll know more than me very quickly if you take a couple of NLP courses, and the field is wide open. There's so much to be done. So we saw some of those applications suggesting next tokens. People who are some kind of disability and they would like to code by speaking rather than typing in, we can use these methods, speech recognition type methods for programmers. Code summarization and retrieval, I'm going to talk about that. You can cast code summarization and retrieval as translation problems. Porting can be cast as a translation problem, porting from Java to C#, that was done by T. Newman and people like that. So statistical models could be used to correct simple mistakes. So if people misspell a word, or just you can use simple n-grams to correct that. So this has been done in English, so we can use the same kind of ideas for correcting errors. We have a project right now using student program data to see if we can do this. Statistical program analysis, that is, program analysis sometimes can be very complex. Many of the algorithms can be cubic or worse. But it's entirely possible that you can guess the analysis results of a program based on the syntax of the program without going through any complex analysis. Because the association between the semantics of a program and the surface structure of a program is probably very statistically skewed. Most people are not going to write programs that mean something other than what they seem to mean, right? So if you read a program and just look at the surface of the program, the meaning should be obvious. If it's not, it's probably not a well-written program. So based on this, intuitively, it seems that we can do static analysis very quickly by using statistics, rather than actually going through and performing the analysis. We can sort of guess what the analysis properties are. And finally, if people are working on this, but I don't have any good progress to date. If you have a way of running language models generatively and sampling programs, then probably most search-based methods would work very well, because rather than sampling programs using genetic search, you can sample them using something like MCMC or Gibbs sampling. If you have a good model, you can sample programs effectively and make it work more efficiently. Right, so a couple more things, examples that I wanted. I think more time, right? About half an hour, 20 minutes?
20 minutes.
20 minutes, okay, all right. I think I should be easily able to do that. All right, so summarization, right? Programming language summarization can be beautifully cast as a translation problem. So translation is huge. I mean, it's enormous, right? So, so here we have two lovely people, Donald Trump and Marine Le Pen. Right, so we have a translation problem, right? So Marine Le Pen presumably likes to speak French, so she might go to Donald Trump and say, "Comment allez-vous?" Right. Now, Donald Trump, of course, he doesn't care about French. Right. So so when I so So when I was starting to study English, and I went to my grandfather, when I was 5 years old, and I was trying to learn English. I'd only spoken Tamil until that point, and I got dumped in an English medium school where everything was English. And I was complaining about, why does this all sound so strange? And why doesn't everybody just speak Tamil? I was just, 5-year-old boy. So it seems strange to me that why is everyone in the world not speaking Tamil? Why do they have to speak English? Why do I have to learn English? And my grandfather told me, no, don't worry. Everybody in the world thinks in Tamil. Their head, their brain is always thinking in Tamil. It's just when they speak, it comes out funny. Yes. But for a little boy, that was the right thing to hear, right? So everybody speaks in Tamil. They're thinking in Tamil. You're all thinking in Tamil, but when we speak, it comes out funny in Italian. Right? Okay. So Donald Trump is saying, okay, of course she's thinking in English. Everybody thinks in English. Everybody, not English, American. Everybody thinks in American, but it comes out funny in French. Right? So what he's saying is, what is the most English sentence she's trying to say? If only she was, smart enough, she would be speaking English. So that's what Donald Trump is saying. So what is the English she's most likely trying to say? So she's saying, okay, maybe she's saying, when she says come on, maybe she's saying, come on, good. And then eventually he figures it out, right? He says, oh, okay, all right, I know what it is now, okay. So then he says, okay, so I'm fine, how are you? And then, of course, Marie Le Pen, she knows everybody in the world thinks in French. This is Marie Le Pen's theory. The whole world is thinking in French. But it comes out in English by mistake. Right? So she's going to go through the reverse process to translate back from you all know who Marie Le Pen is, right? Okay. All right, so this goes, not every American would know who Marie Le Pen is, but so this goes back and forth. Okay, so this actually is at the heart of most modern translation algorithms. It is called the noisy channel problem. Okay, so if you want to translate a French sentence to English, what is the most likely English sentence given a French sentence? Use this what is called the noisy channel model. It's just a normal Bayes equation, right? So what this says is, what is the most likely French sentence given the English sentence times the probability that this is an English sentence divided by the French sentence that was actually said. So if you maximize this probability and you select that English sentence, that will be the most likely translation. Okay, so this is the way most translation algorithms work. All right. So what happens here is you essentially have to estimate the models on the right-hand side. If you have good models for the right-hand side and a good search procedure for searching out the most likely English sentence, you need a good search procedure and a good model. Then your search will be more efficient, right? Then you can produce the English translation. Okay. So PE. That's the probability of an English sentence. We know how to get that, right? We know how to get a probability from the English sentence. Just need an English corpus. No problem. Get an English corpus. You can get a very good model to predict what's a good English sentence, what's not a good English sentence. No problem. Okay? Just get that from a normal language model. Okay. Now, what we need also is the most common way to mess up an English sentence into a French sentence. So, conditional distribution of a French sentence given an English sentence. We need that. Where do we get that? Well, it turns out there are two places to get that. One is the Canadian Parliament proceedings. The other is the European Parliament proceedings. And then, of course, you have the Bible, you have the Quran, you have all kinds of places where you have sentence-by-sentence alignment of English and French. Right? For every English sentence, you have a French sentence. You have the Bible, you have the Quran, you have the European Parliament. European Parliament produces gobs of stuff in multiple languages, right? And it's all aligned very closely, especially when the parliamentarians are speaking, every sentence is translated. So you have alignment at the sentence level. Right? So for every English sentence, you have a lot of data on how to estimate these models. Okay? These models all have various details in them. I'm not going into all the details, but there's lots of technicalities of how this is modeled, right? Okay, so, and the denominator is just normalizing constant. So once you have the numerators, the two numerators, you don't have to worry about the denominator because the French sentence has already been set. It's already been uttered, so you just maximize the numerator. You don't have to worry about the denominator. Right? So we have these two models, and that's how translation works. From this point on, once you have those two models, it's all search. Right? And they use various kinds of optimized search to find the most likely translation. So, in the simplest way, think about this, right? You just have the F given E, have it at the word level. You take every English word, you take every French word in a sentence, in the given sentence, You substitute, look that up in a French to English dictionary and put an English word there. Do that. Now you have a bag of English words which are in no recognizable order. You just keep permuting them until the PE, the English model, says that looks like an English sentence, right? So, you know, for example, in German you have this kind of Tecamolo order, right? Temporal, modal, causal, and whatever, right? You have this Tecamolo order, which is very strange for English speakers. You take all the words in German, you substitute English words, you just keep jumbling it up until the English language model says that looks like an English sentence, and then you're done. Believe me, that's almost exactly how these translations work. Right? Okay? So that's all there is to it. Alright? So that's translation. So why am I telling you this? Okay, so I think we talked about this, right? English language model comes from English corpus, comes from Latin corpus, and then we get the translation. Okay, so now, consider an entirely different noisy channel model. Okay? We have an Android application, we want to port that to iOS. I'm not making this up, this has actually been done. Right? So we have an Android code fragment, we want an equivalent iOS code fragment. We want to do this porting. Okay? So how can we do this? So the idea is, so along comes Marie Le Pen and she says something in Android. Okay, some of you have seen Android code will recognize that. Okay, and so Trump says, okay, she's trying to speak iOS code, but somehow her brain is messed up and she's speaking in Android. Okay, I want to change this from Android to iOS. Okay. What is the most likely iOS version of the code? What is the code that is most like iOS code, that is most likely to have been distorted into Android code in this way? Okay, and then he comes up with the equivalent iOS code. Okay? So this is the basic idea. Alright? So now, it's the same damn thing, right? All we have to do is to find out ways of estimating these models. It's really the same problem, right? There are complications about how you evaluate whether something is correct or not, but it's really the same kind of problem, right? So where do we get these bits from? Where do we get this from? Where do we get a language model for iOS? From iOS corpuses. Go to GitHub, find all the iOS applications, estimate a model, we're done. Okay. Where do you get this?
Apps available for both platforms.
That's right. Any application that's available on both platforms is fine, except you need alignments. It's not enough to have a whole application. You need alignments at some more finer grain. Because otherwise the probability distributions are hard to estimate precisely. This whole iOS application is the same as this whole Android application, right? So it turns out there are actually quite a few applications that have method level alignments. So there are, on GitHub you can find a lot of parallel applications in Android and iOS which have method level alignments. So there's the same methods with the same name. Who knew, right? And there's a lot of this is available in GitHub, so you can estimate these models. Okay? So, right, so model of iOS and an Android iOS joint corpus. So both of those are available. And of course, again, that's a normalizing constant. Okay, so you can actually get this. So in fact, this is being done. So this is a group from Iowa State, and this is a very productive, very creative group. Done a lot of really fantastic work. By the way, they've written a number of papers which are all the same name: Nguyen. And there's an interesting history. It turns out in Vietnam there was a time when there's actually two very common names. I forget what they are. There's Nguyen and there's something else. And it turned out to be sort of a tribal thing about 500 years ago. If you're a Nguyen, then the other Nguyens would protect you. And then if you were not, then the other people would try to have quarrels with you. They'd be fighting and wars and people getting hurt and all this. So most people picked one of these two names, Nguyen or another name, so they'd be defended by the thing. So a lot of people, it's like almost like a tribe. It's not really a tribe, but that's why the names are so common. There's very high, low entropy distribution of names. Okay. So this is what they did. So they trained method level aligned Java and C# corpus they used to train it. And then they evaluated using BLUE. So BLUE is the scoring mechanism that's used in natural language translation. Essentially, what they do with BLUE is that they take human translations, they take the machine translation, and they compare the two, and they see how many tokens are different. So BLUE is essentially a measure of the percentage of tokens that are different between the human-produced translation and the mechanical translation. Right? So obviously, that's very controversial in this setting. That's what they used, because that doesn't mean necessarily that it's going to compile. It doesn't mean it's going to be the same semantics. There's no things like that. So there's been a bunch of follow-on work. And the follow-on work essentially doesn't translate at the token level because their translations work at the token level. And there's measure at the token level. The follow-on work is based on syntax-based translation. So basically they translate certain syntactic constructs directly to syntactic constructs. And that essentially guarantees that whatever is produced on the iOS C# side is syntactically correct. So the Nguyen and Nguyen work doesn't guarantee syntactic correctness, whereas this new work, this is from Switzerland, from ETH group, they actually guarantee syntactic correctness. So it's follow-on, inspired by that work. Okay, so I have one more thing to talk about, and then we'll, if you have time, we'll get into language modeling stuff. So this is code deobfuscation. So this is work from the ETH group. So this is Bialik. The top is Bialik, and then there's Rechev, there's a grad student, and Rechev is the faculty member. Okay, so they're looking at this problem. So you have code. So you have obfuscated code in JavaScript. So in JavaScript, anything is open, anything is source available. That is, all the JavaScript code is available in source. Why? Because to use it, you have to have source code. So most of the browsers execute source code directly. So anything you write in JavaScript has to distribute in source code form. So this has two problems. One problem is compression. That is, when people write programs, they tend to use verbose descriptive variable names, and that increases transmission time, also increases loading and interpretation time, so it's slower to run. The second problem is that, if you have something that is very special and beautiful and whatever, and you would like to make some competitive advantage out of it, that you don't want your competitors to use this kind of special JavaScript features that you spend a lot of time developing, you would like to keep it secret. So you would like to make it harder to read. How can you make it harder to read when the source is always available? Well, the best you can do is to mess up the variable names. Right? So there's a few of these tools available which will take a JavaScript program and mess it up. So on the left you have there an example of a JavaScript program that's messed up. This is not as bad as it can get. It can get a lot worse than this. But this is kind of messed up JavaScript code, right? And so what the problem is to take this and turn it into clear code that looks like that. Okay, so I don't know why this is not showing all at the same time. There's something wrong here. Not showing both at the same time. Okay, sorry about that. So you can see here that between the two, and then this one, you can look at the names, right? Some of the names are single letters, some of the names are not. Okay? And you can see the deobfuscated name. All the names are meaningful, right? So in the obfuscated version, for example, the method name was FZ. Right? And here the method name, in the deobfuscated version, the method name became chunk data. Right? So some of the names were compressed in single letters, some of the names were not. So are all the names obfuscated, and why not?
So you can't obfuscate an API call.
Yes, you cannot obfuscate the API call. It has to be the same because the interpreter has to know what to execute, right? So you cannot obfuscate things like push and length. Can't do that. Okay. So are the choices of the clear names, when you deobfuscate, right? The choices of the clear names are not independent, right? So, for example, if you change this, you look at var r, this here, r equals e dot length, right? So this R, when it got defuscated, became len, okay? And everywhere that R was used, you now use len. So for example, here len is used, here len is used. So the names are not deobfuscated independently, right? So the other question is like, what are the clues for clear names? Why did they decide that this R should become len? Why did they decide that? Why did they decide that this variable? By the way, this is what the tool does. For example, E here, when it got deobfuscated, it became str. So why did they make E into str and R into len?
API output.
Yes, so the API was length, so they figured it's calculating a length of something, so maybe it's a string. And since it's calculating a length, the result should be called len or something like that. So then the clear names give them clues as to what names they should pick for the obfuscated names. So essentially they're starting with the API names. They're starting with the way the obfuscated names are used with the API names. And they're using the API names to guess what the obfuscated name should be. Okay? So that's what they're doing. Now, how can they do this? They can do this because there's a lot of clear code of JavaScript. You can find a lot of clear code of JavaScript, right? As much clear code as you want. There's plenty of JavaScript code on GitHub. That allows you to see what variable names should be and how those variable names are associated with the API names, right? So you can essentially build a model of how API names should be associated with variable names. So once you have this model, when you have an obfuscated name, you still have the API name. So you can try to guess what the clear name should be, right? So that's what they were trying to do. Is that clear? Okay. Right. So what they do here is something called structured prediction. Okay. So they use something called conditional random fields. So we're not going to have time to go into all the details of it, but this is the basic idea. So the idea is here you have a bunch of API names, right? These are given. Even in an obfuscated program, you have access to the API names. You know what the API names are. You know, length, push, pop, those names are there, right? So you know these. What you're trying to do is to guess what the obfuscated name should be. Right? So you need a model that gives you this distribution, right? Now the idea is that in most real unobfuscated Java programs, this is a very low entropy distribution. Once you know the API calls, there are not that many choices that you can pick for the variable names. Most of the time, these variable names are pretty well predictable, right? So then what you can do is once you have this, you run a search algorithm. The search algorithm, given the API names, tries to pick the highest probability names for the obfuscated variables. And you know, most of the time it can do a pretty good job, right? So that's because this distribution is very easy. So that's the basic idea. So I'm not going to go into all the details of conditional random fields, but just to give you an idea. So the simplest kind of model that everybody's familiar with is a regression model, right? Either logistic regression or some other kind of regression, where you have a dependent variable and a bunch of predictor variables, right? The only dependency is between these predictor variables and the dependent variable, right? This dependent variable depends on all the predictor variables, and generally speaking, we assume that the predictors are independent of each other. In fact, in logistic regression or other kinds of regression, if the predictor variables are dependent on each other, you have variance inflation. It's a really bad thing, right? You don't want that in regression models. You want to make sure that the predictors are independent. So this is the simplest kind of model, right? And then you have hidden Markov models, but there's a very simple kind of dependency between the responses, right? So the responses basically are dependent only upon the previous state. They're not dependent upon anything else. So the hidden state is dependent upon the previous state. And the observations are considered to be independent of each other, right? The observations depend only upon the states. They don't depend upon each other, right? And the states depend only upon the previous state. So the simplest kind of state, hidden Markov models. If you have enough data, you can estimate these dependencies between states and previous states, and between observed symbols and the states themselves, okay? Conditional random fields are basically a generalization of this, right? So in conditional random fields, in our case, for example, we have basically all these sorts of API calls that we have dependencies on each other. This API call that we assume this other API call. And then you have the actual variable names, the clear variable names that should be used, that depend upon the API calls. So this is sort of it's a sort of a progressive, greater generalization from logistic regression to hidden Markov models to conditional random fields. At the end of the day, it's the same game. You're trying to basically build a model, conditional model of the variable names based on the clear API calls. You know what I'm talking
Wait.
about? Okay.
Right. Now it's 12:31.
Oh, okay. Should I stop or?
Yeah.
Okay.
Oh, sure. I mean, we are interested, but we have just 1 hour time.
Okay, I don't want to
So
go over.
maybe-
Okay. So yeah, we can see. I can put the slides up and you can see more about this. Thank you for your attention.
Okay.